Going on page 68 when we're done. So today we're going to look at the rational root theorem and Descartes' rule of signs. It's going to help us factor or get our solutions to polynomials when we aren't given one, because we can use synthetic division if we're given one, but if we're not given one and we can't just factor it, we're going to use this. So here's your little family tree of numbers. It's not the entire family tree of numbers, but it's the ones that are important to us. You need to understand that the numbers that we work with most often, rational and irrational numbers, and we also work with imaginary numbers, they all live in the complex number family. All right, so all the numbers that we deal with are complex numbers. They can always be in this form where a and b are real numbers, right? So if b is not equal to 0, then we get imaginary numbers like 2 plus or minus 3i, something like that, or just 3i or I, right? That's why I wore this shirt today. It says, I am complex and I is complex. And what's wrong with the above sentence? And then on the back it says, nothing. Take that, English teachers. Right. So anyway, so I is imaginary, learned all about that in Algebra 2, right? So your real numbers is when b equals 0. That means there's no I in it. So there's your real numbers that you're the most familiar with. Then we have rational and irrational numbers. So what's the difference between a rational and irrational number? Anybody know? Can you give me an example? What? Say that one more time. Which one is pi? Irrational. Irrational is like pi. Okay, so pi is a good example. Okay, what's another example of an irrational number? E. What about like square root of 2? Right? So irrational numbers are numbers that rational, what's the root word of rational? Ratio, okay? So rational numbers can be written as a ratio of two numbers, right? We cannot write these irrational numbers as a ratio. So rational numbers are all numbers that can be written like this. They don't have to be, they can be decimals, but I could make it into this where a and b are both integers. And with your imaginary numbers, when you're doing roots, just remember that the roots always come in pairs. Okay. So it's important for you to know the difference between a rational and irrational number because we're talking about the rational root theorem. Is it possible for you to have irrational roots to an equation, to a polynomial? Can you have irrational roots? Can you have a root that has a square root in it? How do you normally come up with that? Quadratic formula, right? And the quadratic formula usually give you your irrational roots. That's one way to do it. And you could also have roots that are imaginary numbers. But the rational root theorem is only going to deal with our rational roots, right? It's not going to necessarily give us all of them. All right. So here are the two things we're going to talk about. Just kind of summarize it here on the front. So the rational root theorem gives you all possible rational roots of a polynomial. Okay? It gives you all of the possible ones. There may not be any rational roots at all to a polynomial, right? But it gives you a list of possible ones to try, but it's only the rational ones, right? And then Descartes' rule of signs gives you the number of positive real and negative real roots of a polynomial. Two very key differences here. Descartes' rule of signs deals with your real solutions. Rational root theorem only deals with the rational. Now, are rational roots real roots? Yes. Okay, but we have rational here and we have real here. So real also includes what? The irrational. Okay, so the Descartes rule of signs is going to give us rational and irrational roots, but not imaginary. And then the rational root theorem only gives us the rational ones. The rational root theorem is going to give us actual values that we get to check. Descartes' rule of signs just gives us how many. So it's not going to like narrow it down for us as far as which ones or anything. Okay? So those are the two key differences, and then we're going to go look at both of those things here in just a second. Okay? So we're going to start with the rational root theorem. So I put it all there, and it's all of its wordy goodness because I want you to see what this stuff looks like, and I'm going to explain all this to you. So we let this is your generic form of a polynomial, which just looks like a hot mess of stuff, right? But a sub n to the x sub n power, or a sub n times x to the n power, is just your first whatever. So if it's a cubic, then it could be 3x cubed, right? And all the way down to a sub 1 times x to the first, and then a sub 0. So that's just regular. That's the only way to write it generically, which looks horrible. But it says, let this be a polynomial with a degree n greater than or equal to 1. So we have a polynomial. Probably just a cubic and a quartic. Right now we're really solving. We're going to look at a few bigger ones here today. Integer coefficients. Okay, so whole number coefficients. And a sub 0 is not equal to 0, which means we have an actual constant there. Then every rational 0 has the form p over q. P and q have no factors other than plus or minus 1. That means we're going to reduce the fraction. So this just means reduce when we get to do what we're doing. P is an integer factor of the constant term, and q is the integer factor of the leading coefficient a. So we're just looking at the factors of this and this. Right? Just like when you factor a quadratic and you multiply the first coefficient times the constant to see what you got to have multiplied to be, then we're using that same concept here. Okay. Now, the rational root theorem does not necessarily give you the zeros of the equation. It might, but remember, it gives you options. It's only giving us the rational ones. If we also have irrational roots or imaginary roots, those aren't going to show up in what we're doing. Okay. So it gets us the rational ones so we can narrow it down some, and then we can do what we need to do. Today, we're not actually solving anything. We're just figuring out our possibilities and making sense of this stuff. And then tomorrow, we're going to take this and we're going to use it to actually solve stuff. Okay. So if I have this, okay, so if we look at this, it says, what are the possible rational roots of this cubic right here? So we cannot factor it by grouping. We don't know a root, so that we can't do synthetic division at this point. So we're just going to look to see what numbers could we use in synthetic division to check, right? Because if I had something, I don't want to check an infinite amount of numbers, right? And then if I do that, then I'm going to be here all day long trying to do my synthetic division and seeing which ones work. So I'll be able to narrow this down. Rational means that does include fractions. So if you just try a bunch of whole numbers, you may not get what you need there either. Okay. So our leading coefficient in this polynomial is what? 2. Okay. The constant term is what? 5. Okay. Really hard questions, right? All right. So then the only possible rational roots, remember, it's not going to give us all of them, have the form the factors of the constant term over the factors of the leading coefficient. I highly suggest that whatever you have, if neither one of them is 1, or really even if I would only not do what I'm about to do if the leading coefficient happened to be 1, and we'll look at one of those. But when you have this, I would list out my possibilities before I start actually writing my roots. So the factors of the constant term go on the top. What's the factors of 5? 1 and 5, right? So we're just going to 1 and 5. Those are my options, right? And then my factors of 2, 1 and 2, okay? So these are the possibilities for the numerator and the denominator, and I need every combination of them, positive and negative, right? Because if they're going to multiply to give me a positive 5, it could be a positive 1 and a positive 5, or it could be a negative 1 and a negative 5, right? So all of these include all of the plus and minus stuff that goes along with it. So here are the options, and here are my possible roots in my little set. I could have 1 over 1. What's 1 over 1? 1. So plus or minus 1 is an option. I could have 1 over 2, which would be plus or minus 1/2. I could have 5 over 1, which would give me plus or minus what? 5. And I could have 5 over 2, which gives me plus or minus 5 over 2. So that takes it from an infinite amount of possible roots down to 8 possible roots. So if I had to use synthetic division and to check all of these, I'd have to do it at most 8 times. But we're going to be able to even narrow it down from there. Okay? Everybody with me so far? All we're doing today is figuring out what our list of possible roots are, and that's it as far as which ones they are. Okay? Everybody okay with that? Yes? So let's look at this next one. It says, what are the possible rational roots of this? All right, so what is your leading coefficient? 1, and your constant is 10. So remember, this is going to be, it is these factors over the factors of 1. So when your denominator is going to be 1 every single time, You don't necessarily have to list them out like that because all you're really looking at is just the factors of the constant. Does that make sense to you? Because it's just over 1 every single time. So factors of 10 are what? Plus or minus 1. I think the easiest way, the way I think through these every single time, is I start at the lowest, start with 1. And then I ask myself, is 10 divisible by 2? Yes, so it's plus or minus 2. Is 10 divisible by 3? No. 4? No. 5? Yes, so plus or minus 5. 6, 7, 8, 9, no, and then 10. Make sure you don't forget the number itself. I'm saying that because when I was making the key, I totally did that. I had it was one that had like a long list of stuff, and I was checking myself, and oh, look, I forgot the number itself. So, because you're using 1. There's your list. Okay, easy enough? We've narrowed it down. Those are the things that I would check if I was using synthetic division to actually check them to find the roots. And I will remind you of this when I give you the homework, but I want you to hear it from me right now too. On the homework, it tells you to do this, and then it says find the rational roots. We're not finding them today. Okay, all we're doing is doing the possibilities. You're not going to actually go do synthetic division and find any of them. All right, we good? Right, because it would be all of these. Like if I was to list them out like that, I would list out 1, 2, 5, 10 over the factors of 1, which is just 1. So every time it's just over 1 anyway, so I can kind of skip that step. Makes sense? All right, so I want you to try this one. And I want you to do it by listing them out on the little thing right here first, like this, and then put them out there so that you don't miss anything. This one's a little bit of a longer list. Okay, does everybody understand what to do? Okay, I'll give you a second to get that one done. Okay, I fixed mine to actually match yours. Then I've listed out my roots, or my factors rather. And then I would find a methodical way to go through it that makes sense for you. So I'm going to start with 1. So 1 over 1 gives me 1. So it's plus or minus 1. 1 over 2 gives me plus or minus 1/2. 1 over 4 gives me plus or minus 1/4. Okay, that makes sense? It's okay if yours aren't in the same order as mine. Then I'm going to go to 2. 2 over 1 is 2. Then I'm going to go to 2 over 2. What's 2 over 2? 1. I already have that, right? So I don't need it again. 2 over 4 gives me what? 1/2. I already have that. I don't need it again. Then 4 over 1, that's going to give me a new one. That's plus or minus 4. 4 over 2 gives me 2, which I already have. 4 over 4 gives me 1, which I already have. Then I go to 8. 8 over 1 gives me plus or minus 8. 8 over 2 gives me 4. I already have it. 8 over 4 gives me 2. And there we go. Well, you're not multiplying, because it's this factor over this factor. So I'm not multiplying, I'm dividing. On this one right here, I didn't need to because the denominator was 1. But up here, we did the same thing. I did 1 over 1, which is 1, 1 over 2, which is 1/2, right? And then 5 over 1, which is 5, and then 5 over 2, which is 5/2. Okay, and if yours are in a different order, that's okay. Like if instead of doing all of the 1s, if you did all of these over 1 and then all of these over 2, whatever makes more sense to you. I'd rather use up each one of these, or I think I get lost in what I was doing. But okay, we good? And I just said let's make sure we're doing it from like least to greatest. But when it's plus or minus, you can't really do it least to greatest anyway because it changes, so it's fine. Okay, we all good? Any questions? Easy enough? So that means that if I was gonna have to look for roots here, that there are 1, 2, 3, 4, 5, 6. There's 12 possibilities. Are there 12 roots of this polynomial? At most, how many roots am I gonna have? 3, because it's a cubic, right? Okay, but these are 12 possibilities. Maybe none of these work because maybe who knows what's going on, right? Or maybe one of them works and not the rest, because they could be irrational or they could be imaginary roots as well. Okay, are we all good? So we're going to find out what to do with all that tomorrow. Questions? Awesome. All right. Now let's look at Descartes' rule of signs. Okay, so it says let f of x be a polynomial with real coefficients written in standard form. I didn't put that nastiness back on there again. It means basically the same thing. Right, so then when we're looking for the number of positive real roots, remember this is real, not rational, real roots of f of x is either, okay, because you've got some options here, either equal to the number of sign changes between consecutive coefficients or is less than that by an even number. Okay, so it's going to give us, we're going to figure it out, and then it's either going to be that number or something less than that by an even number. So we might figure out that it's 4. So then the answer is either it's 4 or 2 or 0. And that's your answer with the ors. It's like a multiple choice answer almost. And then that kind of tells you some stuff to do with it. Right? And then the number of negative, and again, real, roots of f of x is either equal to the number of sign changes between consecutive coefficients of f of negative x or is less than that by an even number. In both cases, you count multiple roots according to their multiplicity. So if 2 is a root twice, then that actually counts as 2 of them, even in this is what that's saying. Okay. And here's the key, is that it says in both, this theorem implies that 2 tests must be done on a polynomial function to determine both positive and negative. Because we got to look at f of x, which is what we're given, and then we also have to look at f of negative x, so we got to write down what that is so we can make sure we can look at it correctly. Okay? So here's what we're looking at. We've got this polynomial. I don't even care what the possible roots are here. We're just going to look at which ones are positive real and negative real. All right? So I'm going to have an answer for positive real and an answer for negative real. And this is the number of them that I have, not what they actually are. So as I look at this, remember the positive real ones are the number of sign changes between consecutive coefficients, right? So this is a positive 1, positive 2. All right, here we change from positive to negative, right? And then we change back from negative to positive, then positive to negative again, and negative to positive. So we made 1, 2, 3, 4 sign changes. Does that make sense? There's 4 sign changes there. 1, 2, 3, 4. So that means my positive real is 4, or less than that by an even number, 2, or less than that by an even number, 0. It's possible that we have 0 real roots. Or we could have 2, or we could have 4. We are not going to have, even though this has a degree of 6, there are not 6 positive real roots. Okay? Make sense? I didn't do the factors of 4. I went down by an even number. So it's either this number or I have to subtract 2 every time. Okay? We good? Then for the negative one, I have to look at the sign changes for f of negative x. So if I plug in a negative x here, does this say x to the 6th power? Yes. If I plug in a negative x here, does this sign change? Yes. Basically, my signs are going to change when? When do the signs change when I plug in a negative x? When the exponent is what? Odd. All right? If the exponent is even, then it's just going to square it back and it'll be what it is, right? If it's odd, then the sign changes. So here, this is an even exponent. It stays negative 4x to the 4th. This one is odd, so it changes negative x cubed. This is even, so it stays what it is, 2x squared plus 8. So that's what f of negative x would look like. Everybody with me so far? Yes, sir. Because 6 is an even number? Uh-huh. Right, but if I plug in a negative x to the 6th power is going to be a positive x. Does that make sense? Anything negative to an even power is going to stay positive, or it stays whatever it is. So it's only going to change, the sign in front of each term only changes if the exponent is odd. Does that make sense? That is your question? Okay. Anything else? All right, so now we look at sign changes here. So we start off positive, goes to negative, right? So there's one sign change. then it's negative, 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 then it's positive, and there's another one right there. Okay, so it changes from positive to negative, and then from negative to positive. Make sure you pay attention, and I'm saying this because I spent forever yesterday on one, and I don't think it was this one. I was working some other problems trying to figure out which ones I wanted. And I was also finding the roots and stuff, and I could not for the life of me figure out why there was supposed to be two. And I kept looking like there's only one sign change here. It's because I wasn't paying attention to what was going on here. So this is positive, it changes to negative. So that means that there are two, right? There are two negative ones, or how many? 0. There's either 2 or there is 0 because it goes down by an even number, right? All we're doing is counting how many. What that's going to help us with is that if we got that list of what we had 12 possibilities on that other polynomial of what our roots could be, if I go through and I start checking those by synthetic division, if there's 12 of them, that means 6 of them are negative. If I find 2 negative ones that work, I'm done because there's only 2. I don't have to try another one. Does that make sense to you? There's going to be other ways to narrow it down, but you know what your goal is here. So it could be that there are 4 positive real and 2 negative real. There could be 4 positive real, 0 negative real, and then 2 imaginary, right? There's lots of different options of what's going on there. It doesn't necessarily mean that these 2 have to add up to give you 6, because this does not include the imaginary ones. We all good so far? We're just figuring out how many at this point. The rational root theorem gives us possibilities. This tells us how many of each kind we would get for real ones, not just rational ones. All right, so then it says, same thing again. Find the number of possible real zeros and the number of possible negative real zeros for this. So we'll do one more together and then I'll let you do the last one. So I'm looking for positive real and negative real. So for the positive real, counting my sign changes, right? Starts off positive, goes to negative, then it's negative and changes to positive, then it's positive and changes to negative. So how many changes are there? 3. So it's 3, or goes down by an even number, 1. If that goes down by an even number, then I'm at -1, which makes no sense, which means there is at least 1 positive real root here. Does that make sense to you? It's either 1 or there's 3, but there can't be 4 even though it has a degree of 4. Right. Mm-hmm. Yes. Okay, so now we're going to look for f of negative x. So we'll only change the sign on ones that have powers that are odd. So that's equal to positive 2x to the 4th still. That's a negative x cubed, which means that changes to positive x cubed. That's a positive 3x squared, so it just stays positive 3x squared, and then -1. And then I think this is what you were asking me about anyway. So now look for sign changes. It starts off positive, stays positive, stays positive, stays positive. Then from here it changes from positive to negative. So how many sign changes is that? 1. So there is at least 1. Well, there is 1 negative real, because there's not even an option here, because you can't get to 0 by subtracting 2. So that's it. There is definitely 1 real solution, negative real solution, and at least 1 positive real solution. Okay. We good? Just trying to figure. These are all the pieces that you got to do before you go do the work, because if you don't narrow it down by this, you're going to be there all day long figuring stuff out. All right, so I want you to work on the last one on your own. That's what I got. Do you agree with me? Yes. Right. Right. It could just be anything. There's not a rhyme or reason to that at all. Okay. You could have at most for any of these 5, right? And then besides that, whether these are all even and this is odd or whatever, it just depends on the function. Okay. We good? Any questions? All right, so now I want you to look at the homework that I gave you, because there's parts of the instructions. We're going to use some of these same problems, all right? So we're not going to necessarily find all the roots on all of them. I do want you to find all the possibilities on these because some different things pop up, and it shouldn't take you too terribly long to do this. But it says list all the possible rational zeros of each function. Then it says then determine the rational zeros. You are not doing that. You are just doing what we did on the notes, okay? Then on the bottom, it says find the number of possible positive real and possible negative real. And then it says, determine all the rational zeros. You're not determining any zeros at all. Just which ones are possible on the top and how many of each are possible on the bottom. Does that make sense? So don't go trying to actually find anything just yet. And when we do, we're not going to find them all anyway. Okay, we good? Any questions? All right, so I handed you this and I gave you your test review. I will do a video for that before the test. It won't be done today, but and I'll give you some papers back and your quizzes back tomorrow. Okay, we good? All right, awesome.